These reactions gradually remove carbon dioxide from the atmosphere, helping to bring Earth's climate back into a more stable balance. Then came the oceans. During the Snowball Earth period, they were mostly cut off from the atmosphere, stratified, low in oxygen and stagnant in many areas, but as the ice melted, oxygen began to mix in again, along with a surge of nutrients. These included vast amounts of iron and phosphates that had built up in the deep ocean. As they reached the surface, they sparked what scientists call ocean fertilization, a rapid increase in biological productivity. Microbial life flourished. Algae bloomed, bacteria multiplied, and photosynthesis accelerated. In many ways, it marked the planet's first major biological expansion. Picture the oceans turning a murky green, filled with life. Microscopic, yes, but alive, active, and abundant. And this explosion of life had another consequence: rising oxygen levels in the atmosphere. For billions of years, oxygen had mostly been produced by cyanobacteria and stored in rocks or trapped in deep waters. Now, it had somewhere to go and reasons to stay. These dramatic changes in the chemistry of the ocean and atmosphere are clearly recorded in ancient rocks. Scientists can see them in shifts in stable isotopes, evidence of increased carbon cycling. They observe oxidized sediments that suggest a growing presence of free oxygen. And they find thick layers of cap carbonates deposited quickly in the mineral-rich post-glacial oceans. This post-snowball world was turbulent yet full of potential. And amid the chaos, something remarkable may have begun: the slow rise of complex life. Before the Snowball Earth episodes, life was simple, mostly microbial mats and single-celled organisms. Evolution progressed, but very slowly. The environmental shock of a global freeze, followed by a nutrient-rich, oxygenated rebound, may have pushed evolution into high gear. It's a bit like trimming back a tree. The freeze cut things down harshly. But once the warmth returned, life burst back, more vigorous than before. Some scientists even suggest this fertile period helped set the stage for the Cambrian explosion, which would arrive tens of millions of years later. Multicellular life didn't appear immediately after the melt, but the conditions became far more favorable than ever. Earth was warmer, wetter, chemically enriched. Oxygen was rising, nutrients were plentiful. Ecological niches began to emerge. It was as if the planet had started offering golden tickets to a new round of evolutionary experiments. And now, a moment to reflect all of this: the glaciers, the dropstones. The early evolutionary shifts took place on a world without humans, trees, fish, or birds, just microbes, just time, just an ever-changing Earth. It's humbling to realize that our modern world rests on such deep foundations, that every breath we take has some connection to an ancient algal bloom that followed a global thaw. As the planet warmed, it didn't just recover, it transformed. There were still no forests, no dinosaurs, not even jellyfish. But in the shallows of coastal seas, simple multicellular organisms began to appear, soft-bodied forms. Colonial plankton. Early sponges, they were primitive, but they were the first recognizable steps toward complexity. The post-glacial Earth remained volatile. Volcanoes still erupted. Violent storms rolled across the skies. Carbon dioxide levels stayed high for some time, but the Great Freeze had ended. And with its passing came movement, color, and the beginnings of the modern biosphere. Let's also pause to appreciate how much we've learned from this ancient chapter of Earth's story. Snowball Earth has become a vital model in science. It helps us understand planetary feedback systems, how small changes can lead to massive transformations. It illustrates climate resilience, how life endures even in the harshest conditions. It even informs our study of exoplanets' icy worlds that might still harbor life beneath frozen surfaces. In a way, Snowball Earth reveals the fragility of our own moment. It reminds us that climate is dynamic, not fixed. That life is never guaranteed. That stability, while comforting, is always temporary. So tonight, as you wind down, imagine a world just beginning to thaw. Rivers carving new paths. Oceans taking deep breaths for the first time in ages. Microbes dividing, evolving, reaching for something new. In our next chapter, Chapter 7, We'll explore just that, how the curtain lifts on the Cambrian and complex. Life takes the stage, the glaciers have melted, the planet is warming. And for the first time in a long while, Earth isn't just recovering, it's getting ambitious. Welcome to the late Precambrian, a time that feels like the quiet overture before a grand evolutionary symphony. Earth has moved from frozen silence to swirling life, and now something new is stirring. Complexity. This is the lead up to the Cambrian explosion, a moment of rapid biological innovation that begins around 541 million years ago. But the groundwork for that transformation was laid during the warming after Snowball Earth. Let's step back briefly and consider what life looked like right after the thaw. For billions of years, Earth was ruled by prokaryote, simple single-celled organisms like bacteria and archaea, but now something different was emerging. Eukaryotes, cells with nuclei, specialized structures, and most importantly, a tendency to cooperate. And cooperation meant multicellular. Began simply with groups of cells sticking together, dividing labor. Some cells absorbed nutrients, others provided structure. These early collaborations weren't glamorous, but they were the first drafts of what would become animals, plants, fungi, and eventually us. One of the stars of this new era was the Ediacaran biota, named after the Ediacara Hills in Australia, where their fossils were first found. These soft-bodied, alien-like organisms lived between roughly 575 and 541 million years ago. They were flat, frond-like or blob-shaped, leaving behind only faint impressions in ancient sediments. No bones, no teeth, no shells. Just traces. They hint at an early world of experimental life forms. Some look like leaves. Others resembled inflated cushions. Some were discs or tubes. Some shapes defy classification entirely. Were they animals? Fungi? Giant amoebas? Something else altogether? We still don't know, but their presence suggests that evolution was testing bold new forms in this newly enriched environment, following the rise in oxygen, the stabilization of nutrient cycles, and the expansion of shallow marine habitats. Life had room and reason to diversify. Then came the Cambrian. In a geological instant around 541 million years ago, life diversified spectacularly. We call it the Cambrian explosion. But it wasn't a sudden bang. It was more like a cosmic sunrise, gradually revealing complexity. In these ancient seas, animals appeared with shells, limbs, eyes, mouths, and mobility. Trilobites, armored and segmented, thrived. Anomalocaris, a strange, shrimp-like predator with rotating mouthparts, roamed the waters. Other bizarre creatures followed: Wiwaxia, Opabinia, Hallucigenia, each with names as curious as their forms. These weren't just new species. They were entirely new blueprints for life, predators and prey, burrowers and swimmers. Nervous systems, hard parts, sensory organs. Evolution had found momentum and began remixing biology in astonishing ways. To be clear, Snowball Earth didn't directly cause the Cambrian explosion, but it likely paved the way. First, through evolutionary pruning, the global freeze may have wiped out weaker lineages, allowing the survivors to diversify rapidly. Second, through ecological enrichment. Post-glacial oceans were rich in oxygen, nutrients, and open niches. Third, through disruption, massive environmental change opened new evolutionary pathways. It was as if Earth had reset the rules and handed life an upgraded toolkit. From this point on, life became more layered, interconnected, and strange. Predator met prey. Nervous systems evolved. Ecosystems formed. The transformation from a frozen world to a blooming one was more than geological. It marked a biological turning point. Snowball Earth's end launched the long arc of evolution that would one day give rise to forests, flowers, fish, and thinkers. And here's a comforting thought to end on. Every part of you, every cell, every gene, every breath is linked to organisms that survived that great freeze. You're not only made of stardust, you're made of endurance. Of adaptation, of life that once drifted in icy oceans and lived. So as you rest tonight, picture those first complex organisms, soft, slow, and dreaming, floating in the warm waters of the Cambrian. Dawn. Not in a rush, just beginning. just existing, learning to move, to sense, to evolve. The lights were beginning to flicker on, the curtain had lifted, and life was preparing for its next major chapter. That's what we'll explore next. In Chapter 8, the debate melts on scientific controversy. Here, we'll gently step into the world of academic disagreement, slushball theories, and the reason scientists often find themselves debating over ancient rocks. Science, contrary to popular portrayals, isn't about announcing final truths and moving on. It's more like a long-running, often courteous and sometimes not-so-courteous conversation that stretches across decades, even centuries. And in the case of Snowball Earth, that conversation is far from over. The Snowball Earth hypothesis, striking and bold as it is, hasn't gone unchallenged. It's actually inspired one of the most engaging and occasionally heated discussions in modern geology and climate science. Because while the image of a planet completely frozen in ice is compelling, not everyone agrees it happened that way. Let's begin with a deceptively simple question. Was Earth truly a snowball, or just a bit slushy? Enter the competing idea. Slushball Earth? This alternative suggests that, although glaciers likely reached near equatorial latitudes, parts of the tropical oceans may have stayed at least partially ice-free. In this view, Earth still endured a severe ice age, but perhaps not a total planetary freeze. Imagine a world with icy edges and slushy equatorial waters instead of a planet entirely encased in ice. It's a little less dramatic, but potentially more habitable. One major critique of the Snowball Earth model is the life problem. If the oceans were buried beneath kilometers of solid ice, how could photosynthetic organisms survive? How would light even reach them? Proponents of Snowball Earth offer ideas. Perhaps there were thin patches of equatorial ice, geothermal hotspots, or isolated refuges where life could endure. But critics argue that such a thick global ice cover would likely have been fatal for light-dependent microbes near the surface. The slushball model, on the other hand, allows for more opportunities, literally more cracks for life to persist. Then there's the issue of ice thickness. A full Snowball Earth would require ice sheets as much as a kilometer thick at the equator. That's an enormous volume of ice. It raises questions about whether such massive ice coverage could even form without completely halting the planet's hydrological cycle. Rain, snow, evaporation, all the processes that keep Earth's climate moving. And if the oceans were fully sealed, how did enough carbon dioxide accumulate to trigger a thaw? Wouldn't the thick ice layer have reduced volcanic outgassing or slowed the buildup of greenhouse gases? These are legitimate questions that many scientists are still trying to answer. Some researchers also point to inconsistencies in the geological record. For example, sedimentary rocks from the Snowball Earth period in certain regions show signs of regular weathering, evidence of flowing water. Other layers seem to reflect repeated glacial advances and retreats, not a single continuous freeze. These hints suggest a more complex climate system than a static, frozen world. Still, supporters of the Snowball Earth model offer strong counterpoints. They argue that life could have survived near hydrothermal vents or beneath thinner sections of ice. Volcanic CO could indeed have built up over millions of years, eventually producing enough warming to break the freeze. And many of the so-called contradictions in the rock record can be explained by local variations in geology, plate tectonics, or later modifications to the sediments. There's also a case to be made for simplicity and explanatory power. The Snowball Earth hypothesis neatly accounts for the global distribution of glacial deposits, the sudden appearance of cap carbonates, and the distinct chemical shifts observed in rocks from that era. But ultimately, this isn't a matter of one side being completely right and the other entirely wrong. It's a reflection of how science works. Science thrives on doubt, on close examination, on asking, what if? And then chasing that question with fieldwork and data. Snowball Earth is a perfect case study in scientific exploration. It sits at the crossroads of geology, climate, science, biology, and even planetary studies. It's a mystery scattered across billion-year-old rocks, with no easy answers. It's the kind of puzzle that drives scientists to faraway outcrops in Namibia, or to remote icy hills in Canada just to chisel away at ancient clues. The debate continues, not with shouting matches, but with sediment samples, isotope data, and late-night conversations over lab notebooks and core scans. Even now, as new technology and better models improve our understanding, scientists continue to wrestle with the big questions. How many snowball Earth events occurred? How complete was the freeze? What conditions led into it, and what came after? Some even wonder, could it happen again? Don't worry, it's not something we're likely to face soon. If anything, we're headed in the opposite direction. Unfortunately, still, even if we never know exactly what the planet looked like 700 million years ago, the value of this debate is immense. It sharpens scientific tools, it stretches the imagination. It challenges us to think more deeply about what makes a planet habitable and how narrow the line can be between a thriving world and a frozen one. So tonight, as you settle in, think of Earth not just as a place, but as a puzzle, a billion-year riddle wrapped in layers of stone, slowly unraveled by dedicated minds. Scientists working together and sometimes disagreeing, gently peeling back the layers of our planet's ancient past. And in Chapter 9, we're about to explore why Snowball Earth still matters, not just to scientists in labs, but to all of us living on a fragile and constantly evolving planet. At first glance, Snowball Earth might seem like an ancient oddity, a relic from deep time buried in billion-year-old rocks, studied by geologists with wide-brimmed hats and dusty notebooks. But if you look closer, you'll find that Snowball Earth is more than just a frozen chapter in Earth's history. It's still relevant. Perhaps more now than ever. Let's start with the broader perspective. More than anything, the Snowball Earth hypothesis gives us insight into how Earth's climate system behaves not just under normal conditions, but under extreme stress, because this wasn't just a cold period. It was a global transformation. Oceans froze, the water cycle stalled, and life struggled to hold on, then it reversed. The melt was so intense. Temperatures at the poles may have reached tropical levels. It's a story of feedback loops and climate tipping points, of fragile balances that can be disrupted with the right amount of pressure. And that has very real, very current implications. Today, our climate is changing, this time not due to ancient tectonic shifts or dimming suns, but as a result of our own activity. Greenhouse gases are climbing, ice is melting. Global systems are shifting. Understanding Snowball Earth helps us ask important questions. What happens when feedback loops accelerate? How does Earth react to sudden atmospheric shifts? What are the long-term effects of disrupting the planet's natural balance? In this way, Snowball Earth becomes a kind of climate stress test, a demonstration of both the resilience and sensitivity of the system we all rely on, but its relevance doesn't stop there. Snowball Earth has also become a valuable model in the search for life beyond Earth. Let's think a bit more broadly. In our solar system, icy moons like Europa and Enceladus are frozen on the surface but may have liquid oceans underneath, oceans that could host warm hydrothermal vents and perhaps unfamiliar forms of life. It's a scenario that echoes our own past. Just as life on early Earth might have survived by clinging to geothermal vents beneath the ice, life beyond Earth could be thriving in similar hidden habitats. Astrobiologists often look to Earth's extremes like Snowball Earth for guidance when imagining what life might look like elsewhere. In this way, Snowball Earth serves as a reference point for resilience. If life could survive on a planet encased in ice, maybe it can survive elsewhere too. Maybe it already is. And that brings us to something a bit more reflective. Snowball Earth reminds us that life is persistent but not indestructible. That complexity is hard-won. That warmth, stability, and breathable air aren't guaranteed. They're temporary and interconnected gifts. It's easy to forget just how much our planet has changed over time. It has faced fire and ice, mass extinctions, drastic transformations, and surprising recoveries, but remembering those moments helps us understand the present more clearly. When we study Snowball Earth, we're not just looking at a distant past. We're learning how planets function, how ecosystems persist, and how life adapts or fails under pressure, and maybe in a quiet way, We're learning about ourselves, because every plant, every animal, every fungus, and every human being descends from organisms that survived that long, frozen era. We are the result of that survival. We are what came after the thaw. So tonight as you rest, consider this strange and beautiful truth. The earth has frozen over. It has burned and flooded. It has approached the brink more than once, and yet, here we are. Snowball Earth didn't wipe out life, it reshaped it. It tested it. And ultimately, it helped give rise to the complexity we see today in coral reefs, in trees, even in your own hands. As we prepare to enter our final chapter, we'll leave the ancient past and return to the present. We'll ask what this icy chapter can teach us in a warming world. So close your eyes and imagine a quiet planet, once frozen, now spinning gently through space, carrying with it both the memory of ice and the promise of life. And in this way, we've come full circle, from a shimmering frozen world to one rich with life and complexity. From silence, broken only by glaciers, to the lively diversity of ecosystems today, Snowball Earth wasn't just another page in Earth's geological story. It was a test, a challenge that nearly erased life, but perhaps made it stronger, more inventive, and more adaptable. Tonight, we've traveled hundreds of millions of years into the past. We've explored ancient ice ages, submerged oceans, volcanic eruptions, the aftermath of the Great Thaw, and the early signs of complex life. We've walked through scientific debates, pieced together clues from rocks, and imagined icy exoplanets that echo our own ancient Earth. But maybe the most lasting lesson Snowball Earth gives us is one of perspective. Our planet, the small blue world we call home, has seen chaos. It has endured extremes. And through it all, life has returned, not unchanged, but alive. That's something worth remembering, especially now. As the climate shifts once again, Snowball Earth reminds us both of the delicate systems we rely on, and the strength that can emerge when those systems are tested. In every cell, we are descendants of endurance. So as you settle into sleep or drift into thought, consider this. Where in the world are you listening from tonight? What time is it where you are? Has this story helped you unwind, or has it sparked a little curiosity? If you're still awake, I hope you've enjoyed the journey and maybe learned something new along the way. If you've already fallen asleep, then I hope your dreams are filled with drifting continents, ancient undersea vents, and snowflakes falling on forgotten oceans before you go or fade off completely. If you found this video helpful or relaxing, I'd be grateful if you gave it a gentle like and subscribed for more bedtime science. It helps the sleepy scientists keep growing and continue sharing the wonders of the universe, one relaxing story at a time. Thank you for spending this time with me through the cold and the warmth, the stillness and the thaw. Good night, and may your world stay warm and wonderfully curious.